A very good afternoon to all of you. My name is Dr. S.S. Malik, and I welcome all of you to this webinar on ASH Conveying Solutions. We do have some incredible number of participants who have registered. It's about 250. So thanks for all the enthusiasm and the interest that you have shown in us and in this webinar. So let me just start by introducing who we are and from where we are coming. We belong to Thapar Institute of Engineering and Technology, Department of Mechanical Engineering, and we work in the laboratory of powder flow laboratory, which has been set up a long time back, actually back in 2010-11. That time when I returned from Australia after successfully earning my PhD from the University of Wollongong. We set up the laboratory using the funding from the government of India, Ministry of Science and Technology, and subsequently we expanded the capabilities of our laboratories through various research funds. And we have got pneumatic conveying test facilities. This is one of the largest test facility in the world. This has been sponsored by NTPC. They are the major sponsors of our research and laboratory, and we can convey as high as 60 tons per hour in pressure system and 30 tons per hour in the vacuum system. So these are real large numbers. Not only in pneumatic conveying, we also do a lot of work in powder characterization. So we do have very sophisticated powder characterization laboratory, and you can see some of the pictures on the right hand side of your screen, dynamic angle of repose, static angle of repose, etc. We also work in the area of hopper flow, bulk solid stress, flowability, etc. So in the last 10 years, since 2010, we have invested our time and effort in research, and so that we can come up with solutions that are based on innovation, that are reliable, and that are credible. So that we can eventually contribute to solve the industry problem. So there's a lot of work which has gone before today, and many students, my colleagues, myself, we have been part of this journey. And it's been a very exciting journey, by the way. We have received funding either in the form of research or research project or consulting projects from various organizations, starting from the government departments to NTPC, as I said, very big client for us, a contributor for our lab, and Granitool, Belgium, and we are doing a project with Tata Power now, then Odisha Power, Aditya Birla, Reliance, and HPGC, Haryana Power. Right, so over the years we have done fair bit of work in the industry, but we always wanted to do some high value work for the industry, high value in terms of giving solutions to the industry problems in a big way, and that's been our aspiration, that we not only wanted to do research, we wanted to do research for the benefit of the Indian industry, and for the benefit of the society, and quite consequently, you know, last year 2019, actually the government of India has come up with a national innovation and startup policy for the students and faculty in the higher education institutions, and basically the government said it's time for us to bring your technology that you have researched on, bring it to the benefit of industry. And we took the lead from that, and we have developed our own company or the startup within the university campus. So it is supported by Thapar Institute of Engineering and Technology. So we are right here within the university campus, and we are in the area of powder handling, providing powder solutions. So we are Bulk Solids Innovation India BSII Private Limited. It is a university-based startup, and we are incubated. We are very much on the campus of Thapar Institute of Engineering and Technology, and we are right now in the area of designing, troubleshooting, and providing EPCM solutions for industry. And I'm very, very excited to tell you that last week we also received, in fact, last couple of weeks back, we also received a grantinate from the government of India. So our company BSII has received funding from the government of India, and the government of India has decided to fund us for 2 years so that we can commercialize our solution, we can scale up our capabilities, and we can reach to more industries and give them the solution. So I'm extremely thankful to government of India for their generosity and support. Being at the university actually helps us in many ways, and not only it helps us, it helps the industry also in many ways, because we are embedded in an ecosystem which nurtures creativity and innovation. We work with our students, PhD students, master students, our faculty. They are continuously round the clock. We are working to develop new technology and making it more cost effective. And being at the university, it helps us to develop solutions that are reliable, credible, and there is always an integrity in the solutions. Just the way universities work. That's the institution for you. So Bulk Solids Innovation India, once again, that is embedded in Thapar Institute of Technology, Engineering and Technology campus. And today, by the way, we have 3 speakers. So let me just introduce us. So I start with myself. I am the director of Bulk Solids Innovation India. I am Dr. S.S. Malik once again for you, and I am a full-time associate professor at Thapar Institute in the Department of Mechanical Engineering. I have done my PhD in dense phase pneumatic conveying under the supervision of Professor Wipich, who is actually one of my very close ally and my guru, and he's also going to be the next speaker. I have total 18 years of industry experience in material handling. I started my journey in industry as a coal handling engineer. Subsequently, I worked in ash handling. I myself have conveyed 25 different ash samples, from air preheater ash to ESP fast field ash to remote silo ash to very fine ash, third, fourth field onwards. So I have got a lot of first-hand experience of conveying in our laboratory in pressure as well as in vacuum system. So I do understand how the products behave at a very fundamental level, as well as practically. Over the years from Thapar, we have done 15 plus powder handling projects, and some of those industry associates I have already shown those their names to you. And across the world, I travel, and I have given 50 plus invited lectures over last 14 to 15 years. My second speaker is Professor Wipich. He's a senior advisor of our company Bulk Solids Innovation in India. I'm extremely glad that Peter is with us. He's a full professor at the University of Wollongong for last 40 years. He's also the director of ISRI, which is an independent institute within the university. He was the forefather. He was the pioneer. Let me tell you, he was the pioneer who brought dense phase pneumatic conveying in Australia, and then subsequently he spread that technology throughout the world. Just like me, I have come to India with that technology 10 years ago. So through his students, the technology is now all over the world. So the very reliable and capable Australian technology, but of course we have customized it for the Indian requirement. He has more than 40 years of experience. He has done more than 50 ash projects. Our third speaker would be who will come to the end of the show is Mr. D.S. Malik. He is also another director, so I'm extremely happy that he's now decided to work with us. He has worked in DCPL and DCIPS, very reputed firms, for more than 45 years. He has been the executive director and head of mechanical engineering department. DCPL, being such a reputed organization, you can understand, has worked with various clients over the years, such as NTPC, various state boards, and he has also served as the committee member for Indian standards. Now he's also a visiting professor for Jadavpur University. In fact, he has been doing it for last 20 years. He also does have a lot of interest for serving industry. Of course, that has been his primary job, but also he doesn't mind spending time with the next generation, building them up. So the agenda for today is we are going to see what are the root causes of failure. Number one. Number two, what could be the solution options? Then Peter is going to talk about blow tanks. That's a feeder for ash conveying in pressure system. Then finally, we are going to take certain questions. Now, because we are doing on a webinar mode, so all you have to do is you just have to type up your questions, and we are going to take certain questions at the end of the session, towards the end of the session. All right. So with this, I have finished the introductory part, and I hope now we are all ready to go for the first talk of today, which is 15 plus hidden causes of for non-performance of pneumatic ash handling systems. So there are many reasons why your pneumatic conveying system may not work, and we'll come to that. And we'll also see what are the diagnostic tools and solutions. All right, so let me just come to this slide. All right, so what you see is typically, let's start with the basic, that what are typically the plant requirements. Typically in the plants we have a vacuum system under the ESP hoppers, and they suck ash, let us say just some numbers I'm giving, at 60 tons per hour, and they put the ash in buffer hopper, and from that ash actually goes to the remote silo. I've just put some numbers. For example, let us say the vacuum system capacity is 60 tons per hour each, and then the pressure system capacity is 120 tons per hour. Now, the whole reason why we are here today is because everything doesn't work properly. And when you ask the plant people, the owners of the plants, that what are their problems, and they typically say we have undercapacity, and those are the problems they get. We are not getting sufficient tons per hour. We also get frequent line blockages or occasional line blockages, and because of this, all these reasons, the ash level in the ESP hopper goes up and up. And when you ask, what do you think about the commonly thought reasons? What could be the ones giving you the trouble? So often people say that this is the small compressor, or maybe my vacuum pump is small, or maybe the pipe diameter is small. So things are quite small. So that's why probably I'm not able to get the numbers. But let me tell you also, it's not just 3 or 4 reasons. There are more than 15 reasons for which the pneumatic conveying systems may not work properly. One reason is undersized compressor, which you know, undersized vacuum pump, undersized pipe size. But let me also read out for you, because this slide is very, very important. There could be many other reasons. One is wrong selection of step up location, the pipe diameter. Why do you step it up? People make mistakes. Blow tanks could be small. People often overlook these things. There could be poor flow control in the blow tank. There could be inadequate differential pressure across the blow tank. The fluidizing pads can be quite restrictive. The feeder surface, this is a very simple thing, but people overlook. Feeder surface or the surface profile may not be suitable. They may be very rough. There may be surfaces. Also, the material handling valves may be not fully opening. Maybe some other issues. Then you have flow through the adapter piece. Small things, let me tell you, small things can choke up your entire system. The hopper fluidization may be either inadequate or it may not be working. Air intake valve, vacuum system may be improperly set. Maybe the back filter is undersized. Maybe there are some operational control issues. And finally, there could be some layout issues. So it's a whole range of things which may actually go wrong. Now, let's also understand that why the systems go wrong. And the reason for it is it's not a very easy system to design in the first place, because the particle and bulk properties can vary quite significantly. Ash from one plant can be very different from another plant, from one time of the day and the other time of the day, depending on the load, depending on the boiler condition. Ash can be very, very different, depending on the mill also, the coal mill. Ultimately what you get as output can be very different. The other problem is often the designs are based on assumptions. People use thumb rules, but thumb rules are only thumb rules. They are not always scientific. So overconfidence in these things can go very, very fatal. A little bit more on this. Let's go a little deeper. Particle density, based on our experience can vary massively. So as the loose port bulk density and so as the particle size. You can see that these numbers can change by approximately 2 to 3 times and maybe 1.5 times. So there's a huge variability that you get. And obviously, if you don't design properly to take care of the worst case scenario or a case which is on the higher side, which is towards the worst side, obviously you will struggle. Now, these are some very easy things, the particle size, densities, etc., very broad things, but underlying there are many other things which contribute. Say, for example, the particle shape, the cohesion, size distribution. It's not only the median size, it's the distribution. Fines, how much fines you have, fluidization, deaeration, conveyability, also, and cohesion. So all these things, they contribute to the failure. Some of the things we talk about more often than not. Some of the things they remain hidden. So we have to be very, very careful about it. The another issue is even the stuffs we often talk about, bulk density, particle density, there are different ways of measuring those. You put a little bit of tapping on your bulk density. If it is a fresh ash, you do some tapping, you can compress it by 50%. So your bulk density can change quite a bit. The other problem is we always talk, many times we talk about what is the particle size, but then how do you get your particle size? How do you take a sample of particles, ash? So your ESP has tons and tons of material, ESP hopper, by the way, I mean, but when you get a little bit of sample out of it, it's ultimately what you send in the lab is few grams. So how do you know that your sample is a good representative, the one you have tested? There could be segregation inside the when you have sampled it. So all these are practical issues people overlook. We always talk in simplistic ways, but there are underlying issues how we measure. Do you use a sieve method or do you use a laser diffraction? Your results can be quite different based on that. All right, so now we come to something which we are more familiar of, compressor and vacuum pump selection. So these are the air movers, and we always blame on that these are undersized. Now, first of all, why I require a good size compressor or a good size vacuum pump? Let me talk about compressor. When I ask this question, people always say, if you don't get enough air, you are going to block the line. That's very, very correct. But also there is another reason why you should supply enough air. You have another incentive. You have to understand this, that a portion of the air that you send goes to the blow tank, and it is that compressed air which pushes the material out from the blow tank to your line. So forget about blockage. Blockage situation will come later. But first, are you having enough material coming in the line? If you are not putting enough air in the blow tank, how do you expect ash to come in the line in the first place? So let first ash come in the line, and then we talk about blockage. So yes, one is blockage. You have to get you shouldn't get blockage, very important, but also you need second sufficient airflow, a portion of it which will go to the blow tank and push out the material. Now, of course, this is a very important slide, but I'm not going to talk much on this. Now, this is the core. This goes on at the back. This is where we have spent last 10 years of our effort and journey. We have done thousands and thousands of experiments, and we have got very, very good quality models. So we use a criteria based on Froude number. We don't use velocity to design our systems because we believe that Froude number takes care of the particle pipe diameter effect. So what it means is that when you scale up from a small diameter pipe to a large diameter pipe, you do need to include the diameter effect into that. If you go by the only velocity, you will get blockage. So we use Froude number 4 to 6 for blockage for pressure system, and in vacuum, because the air is thin, so you need extra air, extra velocity of air, or extra Froude number. So we use 8 to 12. But of course, on top of it, you have to put your design margins. So we have done quite a bit of research over the years that you can see through these publications. Now, let me show a very, very interesting study. Now, this is where a lot of mistake is done. We always think that the more is the merrier. the more I give, the better I get. It's not always true, especially in pneumatic conveying. See, what happens is you can see this particular point over here. You can see this point. This is my ideal operating point, and this should be my air flow rate. So I have my mass flow rate of air in the x-axis and my pressure drop in the y-axis. Now these are actually called the pneumatic conveying characteristic, constant ton per hour lines. So let us say I want to have a system having 120 tons per hour capacity. This is what I want, guys, right? This is what I want, and my calculated value of airflow is this one. So this is my calculated value of airflow. So this should be my ideal operating point. But what I have done is I have asked, I have been a little defensive. I don't have confidence in my design. So I thought, let me put a little bit of margin, or maybe I have forced the designer to put a little bit of margin. So what happens is because of all those things, now he increases the airflow. So he actually goes to this point. Now the problem with this point is, as you can see, this point is less than 120 tons per hour. Now you are somewhere around, let me just write it quickly, 100 tons, 10 tons per hour. Why is it so? What is happening first in the first place? Actually, when you increase your airflow without increasing the pressure, actually you reduce your tonnage. Why? Because your the faster the product moves, the faster the ash moves, the more pressure drop it will consume, and also extra air requires extra pressure drop. So so your available pressure for 120 tons per hour ash flow is not there anymore. So you have to be very judicious. So this is whole design aspect. This is where the design comes into play. You have to optimize, and optimization, as we know, is always tricky. Because you really need to know what's happening at the background. Now, the other thing is very simple. When you don't have enough air, enough air pressure, by the way, so obviously your tonnage goes down. So basically, starting with this point, all you do is you have come down to this point, so your tonnage has come down. So it's very simple, rather. So maybe now you're operating at 100 tons per hour. So if you keep the airflow same, as this, and all you do it, you choose a compressor where the pressure is less, so you get less tonnage. So don't always look for the capacity of compressor. Also question how much pressure it is giving. Is the compressor having enough pressure? Pressure and capacity, both are important. Extremely important point this to remember. Or either way, you lose it, you lose the tonnage. It's lower, you lose the tonnage. Another very important part is how you interpret the curves, vacuum system. Now, this is very tricky, let me tell you, vacuum system. So what happens in a vacuum system, the moment you start to lose a little bit of flow, the ash starts to get deposited in the line. And when ash starts to get deposited in the line, let us say, this was your original operating point. When ash starts to get deposited, then your vacuum starts to go up. All right. So the vacuum starts to go up, and you basically come over here. So your vacuum starts to go up, and basically you come over here. So what happens is, as a result, if you start working on this curve, which is a vacuum pump characteristic curve, you come at a point here. The problem is, as you increase your vacuum, the air density goes down rapidly. So you might think that earlier I was working at 3830 meter cube per hour, and now I am at 4000 meter cube per hour. But remember, this is at the suction point of the vacuum pump. So the problem is that, okay, in terms of capacity, you are good, but your density, air density has fallen. So you actually will lose about, in this particular case study, which is a real case study, you would lose about 15% of your air mass flow rate, which is certainly going to block the line. And then you will lose time in unblocking, you will lose time in material discharge valve open and close, your vacuum breaker is going to shut off. And in pneumatic conveying, you lose time and you lose tonnage, and you lose tonnage, you lose generation. That's it, as simple as that. All right, so vacuum system has its own problems, and it's tricky, by the way. It has its own science. The other important part is blow tank operation. People often neglect it. blow tank optimization. Rather, we always talk about the total air, but you really have to see how much of the total air, how they are distributed in the top air, and fluidizing air and conveying air. And you really need to do a good optimization out of those. Why? Because if you give too much of top air, or let me start with the green one. If you give a good quality fluidization air, you will help the ash to flow. If you give too much, if you give top air, and if it is just the right one, your ash flow will be very good. A pre-pressurization, if you can do it, it will also help you to get good flowability of ash. But you also remember there are limits. If you give too much of top air with respect to the conveying air, then you actually block the line, because too much of ash all of a sudden comes in the line and you block it. On the other hand, if you become very defensive and you set things in a way that very little air goes in the top air, then you don't have enough air to push the ash out from the blow tank. So that's another end of the problem. All right. So blow tank optimization is an extremely tricky task, and this can be done at site. But yes, if you know how the physics is working, you can do it at a less time and with more confidence. Another important part is blow tank fluidization. This is one of my favorite topic, by the way. You give a little bit fluidization. Now to do that, you need the right quality of fluidization pad. You need to have the right pad with the right permeability, and you need to put your fluidization pad in the right zone. If you do that, what happens is the friction on the surface becomes very low. So ash can come out very nicely. That's good. That's what we want. The another thing is when air enters, the air would require a path to come out, and that path will be always the lowest path. So it will, on the way, it will actually push the ash out when the air comes out. So a little bit of fluidization can improve the fluidity of the ash, and the ash will come out very nicely. Another important part is you have to create differential pressure across the blow tank. So this is basically your blow tank, and you need to create a DP across the blow tank, because air always would like to take the least resistance path. This is the path air would like to take, but you want some air to come here, some air to come here, and some air to come here. You need to maintain that optimized ratio. Now, unless and until you provide an artificial way to provide a DP, differential pressure, maybe in the way of a nozzle, all the air is going to bypass the blow tank and the product is not going to come out, and you will get less tonnages. So you need to calculate the right amount of DP, because if you don't calculate it properly, you actually consume the total available pressure which is there at the compressor. Another very important thing, blow tank. This is my favorite topic. Blow tank sizing. People always talk about pressure, flow, but blow tank sizing is very important. This is like you are running, and it's not that your blood has to be very pure. It has to be nice, thin, cholesterol free, etc. Your heart has to be big enough to pump for you to gain that same speed. All right, so blow tank is the heart of the system. Please understand that. A small blow tank, with a small blow tank, you can't pump at the same time. So what is going to happen? You pump in, pump out, pump in, pump out. You get fatigue. Just like your heart gets fatigue and it breaks, the same thing will happen with the valves in the blow tank. They will wear out, and all these problems. So there are on-off things, there are valve timing changes, and you like to reduce it. So you should have sufficient size of the blow tank. A very rough calculation, roughly for 100 ton per hour ash flow. Ideally, if I design, I would go for anything between 4.5 to 4.75 cubic meters blow tank, and I don't recommend design 15 discharge cycles per hour. That's my recommendation. Few other things are important, but I think my next speaker, Professor Peter Ripich, is going to cover this part of the blow tank. If you don't have good airflow across the blow tank, this is a top discharge blow tank, and you have this fluidizing pad somewhere here. You can see everywhere you have ash deposited. Why? Because the ash, because the blow tank is not doesn't have enough permeability in the pad, and the ash was cohesive. So this is what you get. So when the air can't come out, it can't push out the ash. It's as simple as that. So not enough fluidizing airflow, ash agglomeration. So you need to really have a very strong hold of how much air should come to the blow tank and what should be the quality of the pad. You have to design accordingly. You can't do everything in the last minute in the plant trial and error. No, design has its own significance. Another problem is arcing. You can see at the bottom of an ESP hopper. This was actually the sixth field, I guess. So the ash was very fine, and you can see it's all choked up. Now, what causes that? It is basically the surfaces over here. So the change in direction. When you have a sharp edge and the surface quality is not proper, you start to build a dead zone. So you can see the dead zones building up. Originally, this was the opening size, and now this much of the size is actually gone. So your pipe effective or discharge size is small, and then after some time, this is what you get. You can't see the opening size anymore. So again, if the ash doesn't come in the line, what are you going to convey? Sometimes people take a very simplistic approach. Instead of having a proper conical blow tank, you can see the blow tanks surfaces have been cut into plane surfaces, and this is what you get. Now every line like this, those lines, those are potential arcing points. So you start to get flow obstructions from there. Now what is it? This is a ESP hopper. You never thought this is a ESP hopper, isn't it? This looks like some hole going to the center of earth. This is actually inside a ESP hopper in a power station. You can't believe it, I'm sure. So what happens is, you see, is it a very plain surface? You can see it looks like the surface of a moon or Mars. So when the ash remains there, you actually get some rat holes actually, and then eventually the surface inside becomes that much rough. So ash just can't come out. So this is another interesting thing. People always many times wonder that my vacuum system is not working. Why? My vacuum pump is big, everything is fine. Why is it not coming? My vacuum is increasing in the first part of the cycle, and then it stops over there. What's happening? That's because you create rat holes. So what happens when you start sucking the ash, this ash over here, it comes out easily, and the remaining ash sits over there, and this is what you call a rat hole. So we have done quite experiments, you can see. So we have given some fluidizing air on the sides, and then initially you can see a lot of rat hole here, but then when we give fluidization air, you can see the rat hole actually has broken. So this amount of ash has started to get conveyed. Vacuum air intake valve setting in the vacuum system, that's another very tricky part, but I'm not going to spend much time on this. You have to optimize the opening. If you excuse me, if the opening size is too small, actually you increase the vacuum, which is good. Actually you get enough pickup velocity at the hopper discharge, but again the problem is then you increase your overall vacuum in the system, which is also not good. So you have to optimize various things. All right, so finally I have come to the end of my talk, and let me just summarize 3 points for you. This is the takeaway in very macro term. I would really recommend, do not see the system and components in isolation. The design of the system and the operation and the design of the components, the choice of the components, the sizing of the components, they go hand in hand, right? And together they can create trouble. So if we have to sort out a system, an overall system, we have to look into both design of the system as well as into the components. Your design in the first place has to be good and cater for the worst situation. Now you have to be very judicious in that, how you do that. And you have to systematically diagnose, do the diagnosis of the root cause. So that's all from my side, and I hope you are typing some questions. And now I am going to hand over to my next speaker, who is Professor Peter Whippich. So Professor Peter Whippich, I request you to come on air. Thank you very much.
Okay, thank you, Dr. Malik. Very interesting talk. I've only got brief time, 20 minutes, to cover blow tank feeders, so I'll try and be as brief as I can to allow some question and answers at the end of this seminar. So blow tanks are pressurized hopper feeders. So similar to ESP hoppers or just normal storage bins and hoppers, well, blow tanks are hoppers, but under pressurized conditions. And blow tanks also should be considered as feeders. Now, many of the problems that can occur in storage bins and hoppers and ESP hoppers, such as funnel flowing, rat holing, material buildup, poor interface design, can also occur with blow tank feeders. Furthermore, if you're trying to predict the flow rate of powder from a hopper, this is quite difficult and uncertain, and several PhDs have been undertaken to try and solve this problem, and it's still largely unsolved. So you could imagine that trying to predict the flow rate of powder from a blow tank under given conditions for a given product, that's even more difficult and uncertain due to the increased complexity of the compressed air or gas. So we need to have, at the end of the day, have good operational control over blow tanks so that we can ensure adequate feed rate capacity and hence system capacity. So the underlying problem, as I see it, my many years of experience, that blow tanks generally appear to be inherently simple or static type devices, but appearances can be deceptive. And many designers and operators do not appreciate the many factors that can affect blow tank performance. So the end result is that often what goes into a blow tank does not come out too well or even at all. So the consequences reduced and inconsistent capacity, incomplete emptying of the contents, and also material build-up, such as dead regions of loose material or products sticking to the walls and roof of the blow tank and so forth. So what I'd like to do very briefly this evening is to describe some of the different features and characteristics of blow tank feeders, consider ways to maximize performance to achieve reliability, the required discharge rate, and also minimize air consumption. And emphasis will be placed on blow tank design, sizing, operation, some of the common problems and solutions I've come across, and the relevant modes of flow here I should highlight at the beginning, at the outset of my talk, for ash handling plants, that ash generally in the industry is conveyed under dilute phase or suspension flow conditions. If the airflow is sort of in the minimum zone, you can what we call medium phase or dune flow. And for shorter distance applications, you can also achieve fluidized dense phase. So I'll use these terms at a few times during my talk. So let's firstly talk about blow tank design. Now, many designs and types have been developed over the years, and these have been developed for specific material properties and applications. So, for example, we refer to one configuration being bottom discharge. It's a fairly common configuration in industry. As you can see here, the product's discharging out through the bottom. We also see in ash handling plants top discharge blow tanks. So the product discharges out through the top, of course, but it begins its journey towards the bottom of the blow tank as well. And right at the bottom here, you have a fluidizing pad to hopefully fluidize the product properly for good complete discharge. But also there's a sort of a hybrid version. We have a bit of top, but mainly side discharge. So this side discharge in this particular case is fairly low, and I have seen a lot of vessels in India where the side discharge is a bit higher. So it's a semi-top side discharge configuration. I generally call that side discharge. And one reason people have selected this type of blow tank is for more to control more floodable type products. So with a bottom discharge, if you've got a heavy free-flowing material, that can rush out into the pipeline, and the side discharge will tend to self-control that. So with blow tank arrangements, the common simple system is a single blow tank. We call this a batch feeder. And one thing I'd like to highlight initially from a design and troubleshooting perspective, the average blow tank discharge rate can be up to 100% greater than the required system capacity. So for a single blow tank unit, if you're looking at a system capacity of 50 tonnes per hour, you'll probably need to discharge the vessel at about 100 tonnes per hour to make up what we call the cycle overheads. And generally for ash handling plants, the tonnages are much higher than that, the distances are greater. So we generally need to, from an efficiency perspective and reliability perspective, we need to pursue continuous feeding and conveying technology. So we can achieve this with twin or multiple blow tank feeders, and these can, the common one is vessels in tandem or parallel configuration. This one here is bottom discharge. You can also do top discharge like this, but here I'm sure you're fairly common with the idea here that one product is discharging, the other one's isolated, and it's receiving material and being pressurized, ready for discharge before the first one runs out. And then you just change the two over. With bottom discharge, you don't get 100% continuous feeding. You may get 90 to 95%. But if you do require 100% continuous feeding, you can go for blow tanks in series, which we also refer to as piggyback arrangement. This is not a common installation. This is one that we designed and installed in a power station in Australia, where the requirement here, this is a top discharge feeding vessel, that we need to achieve 100% continuous feeding. So let's talk firstly about some of the problems and solutions based on my experiences over the years. The components, they're sort of the small things of the system, but quite often the small things make a big difference. And the common complaint that I get from industry is there's quite often a frequent failure of critical components. And these components may not necessarily be quite that big. So perhaps a valve, a seat or a seal is failing quite frequently. And what happens is the entire pneumatic handling system or conveying system gets the blame. And the root cause quite often for these cases is the incorrect selection, installation and or operation of that component. So in the first case, from the design stage, the component wasn't matched properly to the product properties and or application requirements and conditions. And today I will emphasize that components are available that can achieve reliable operation in ash handling plants. So generally with any component coming in contact with the ash, because the ash is quite abrasive, our general recommendation is to go for fast acting full bore valves, and you also need to handle the wear aspects of the product, and also to ensure that the valve is made of a good quality and it's compatible to the product and application. So it's not a trivial task, and you need to make sure you pick the right components for the job. So check your specifications. Second area that people experience problems is due to blow tank sizing, design and operation. So blow tanks, of course, need to be sized and designed and operated properly to achieve the required capacity. That's quite obvious. So to do this, we need to determine the relevant cycle overheads. And this is not easy at the design stage. At the troubleshooting stage, we can go in there, stopwatch and calculate things and measure things. And you can see if those cycle overheads, such as blow tank filling, discharging, venting, purging, all those sorts of things, if those numbers are correct or not. At the design stage, trying to predict the discharge rate of product from a storage bin or hopper. As I said before, this is not easy because of fine powders and air interactions, but it's something that you need to give margin in your design stage. And so you make sure that you can achieve those rates under the different operating conditions. But one cycle overhead that quite often is overlooked is valve actuations. Some of the valve actuators, the cylinders, quite often they get discharged back through the relays, and as a result, the actuation times are too long. And so the cycle, the number of times or the total time for valve actuations can be quite large and significant, and it eats into your system capacity. So be careful with that one. Also, we need to ensure we have suitable blow tank duty. So Dr. Malik referred to 15 cycles per hour. Generally, we operate around 10 to 20 cycles per hour, depending on the application. And make sure also that you have an efficient method for venting and purging. One thing that will restrict your flow of ash into a blow tank is the air trying to force itself way back up into the material flow, and because of the fine powders involved here. So make sure you do have an efficient venting method, because otherwise it can blow out your filling times for the blow tank and your system. Also, it's essential to match your blow tank type and arrangement to the material properties and application requirements. And once you do this properly, you will achieve reliable and efficient operation. So the third area where a lot of problems occur is in the area of airflow control and distribution. So we certainly need to control the distribution of air to the blow tank feeders and the conveying pipeline, as already indicated by Dr. Malik, because this certainly can have a direct effect on system capacity. But we also need to control and distribute the air evenly around the blow tank, whether it's going to the top air, the fluidizing air, the conveying air, or supplementary air, or whatever is occurring for your particular system. And we need to do this, make sure this is working properly for the pressurization cycle. So the amount of air you're putting to the vessel and the line may be different there under those conditions. And when you suddenly discharge, you may need to adjust your airflows to achieve the required discharge rate, because sometimes you need a certain amount of air for pressurization, and sometimes you need a different amount of air when you go into the discharge cycle. So if you don't have that control over your airflow, then who knows what discharge rate that you will ultimately achieve. So these are things that are easily solved, but quite often trying to find that to be the root cause is not easy, because a lot of industrial systems don't have airflow meters. And so quite often we've gone to site, we've had to install some equipment to quantify what's happening, then we can understand what's going on. All right, and the other thing that can affect your airflow control and distribution is your fluidizing device and or membrane. So this also needs to be designed properly to match your product properties and application. So finally, the method of air injection, aeration itself. This is the one area too that we've seen common problems. Can have a significant effect on system performance. So we actually studied this for many years, some decades ago, looking at dilute phase and dune flow and fluidized dense phase. And I'll limit my talk to ash handling plants here this evening. So just to share with you some research findings. So the original blow tank in our laboratories, you can see here, these are 1 cubic meter vessels. So the original one we had was a single blow tank 1. And this is a fairly common single point injection system. On the inside here, we had these rubber flaps that you may be familiar with, I'm not sure, but a fairly common air injection system. So we had top air, we had your aeration air or cone air, and we had conveying air. And we did a lot of ash conveying in the early days for the power stations in Australia. And one thing we did decide to do for this particular blow tank, because we wanted to see what was happening inside the blow tank, so we put a window. So these vessels are rated to 1,000 kilopascals gauge, and we knew also the ash is quite dusty and sticks to glass, so we actually put in windscreen wipers on the inside of the vessel. So it was a clever little design, and actually works quite well. All you need is just a little torch there and little step ladder, and you can see actually what's happening to the ash inside the blow tank. And you learn a lot from actually seeing what's inside the system. And with a lot of industrial systems, of course, you don't have the luxury of doing that. Anyway, so with blow tank 1, we started experiencing a lot of problems, just as we saw in storage bins and hoppers. So the sort of rat holing, funnel flow that you see in storage bins, we also saw inside the blow tank for when we were conveying precipitator ash quite fine. That's quite cohesive. So we came up with the idea of building a second vessel, blow tank 2, with a difference. So we basically reproduced the same design, but we cut off the outlet here at this location, and we put in a fluidizing discharge cone. And we also use top air, and then we use fluidizing cone air and also conveying air. So we were able then, for a whole range of different products, we were able to compare the discharge performance and the performance of the blow tank in general for blow tank 1 right next to blow tank 2 for the same pipeline and same product. So here we see just a photo of the 2 blow tanks. We also had load cells on the blow tank, so we knew everything that was happening in the system, from the feeder through the pipeline and over to the receiving bin. So you can see here the windows. We also use scales here to make sure the blow tanks were calibrated properly, or the load cells I should say. And so we tested these things side by side. So we tested a range of powders, fly ash, a lot of fly ash, some pulverized coal and cement as well. So in just summarising some of the key results. So with the more cohesive powders, we immediately experienced problems with blow tank 1, such as rat holing and incomplete emptying. Also, the discharge rate of all the materials from blow tank 1, I'm talking about all those products we tested, it decreased during the second half of the discharge cycle. And we actually, through the window, we could see funnel flow effect, as you see in a funnel flow bin. We also found with top air, it actually tended to compact the powder bed, even with good fluidization. So this actually tended to exacerbate these problems of rat holing. With blow tank 2, however, we got amazing results. So all the powders, even the cohesive ones, they all discharged evenly and consistently through the fluidizing cone, right down to the last kilo. And so the discharge rate of blow tank 2 was linear right across the full discharge cycle. So this was a tremendous result. And if you compared the two blow tanks side by side, the batch rate for blow tank 2 was up to 30% greater than blow tank 1. And hence, the amount of air you used for blow tank 2 was up to 30% less than blow tank 1, because you're conveying the material far more efficiently. So we saw immediately the need to change that original blow tank to the same design as the blow tank 2. So you can see here now blow tank 1 has got the fluidizing cone as blow tank 2, and this became our test rig for many, many years. And also we used this technology, applied it to industry. So this is the first ash handling system we designed back in the 90s. This is 100 tonne an hour. These are 7 cubic metre vessels. You can see the fluidizing cone here. And this system ran for 20 years before it was shut down and replaced with a classifier. And not one bend was wore out, and the rotating disc valves we used on the outlets lasted for 20 years. Amazing result. It was a true, actually, dense phase system, over 1.5 kilometres, 100 tonnes per hour. So in conclusion, despite the apparent simplicity, blow tanks come in different sizes, designs, types and arrangements. The numerous components and methods of air injection are also available for blow tank operation. So for all these reasons, it's essential to match blow tank design, its components and method of air injection to the material properties and the application requirements. Whether you're conveying for dilute phase, dune flow, dense phase, whether you've got powders or gritty coarse products, the same requirements apply. But once properly selected and operated, blow tank systems can perform reliably and efficiently for many years, even decades, with little maintenance. Thank you very much for your attention. So I'd like to hand control back to our chair. Thank you.
So now we are going to start the question and answer session. And before that, I thank you very much, Peter, for your very detailed presentation. And we have got few questions. In fact, many of the questions are repeated, so I have sort of combined them into similar languages. The first, I'm going to take the questions. Question number 1 is on pickup velocity. So what sort of pickup velocities we should have? But we don't work with, my answer is don't work with pickup velocities. We work with Froude number, which is velocity divided by square root of G into D. This was in one of the slides. Now I'm happy to send you the slides also, so you can see the formula. And we for pressure system, we operate between Froude number 4 to 6 to start at the blow tank location, and for vacuum system we double these numbers, so around 8 to 12. So if you know the pipe diameter, so if you take Froude number 6 and you know your pipe diameter, so 6 is equal to V by root GD. So you can calculate, you put the diameter, let us say it's a 250 millimeter pipe, so you can calculate the velocity requirement. So we go with pickup, not pickup velocity, but pickup Froude number. All right. Second question was that what should be the pipe diameter, or what is the pipe diameter selection criteria? Now this is basically you have to do few iterations. On diameter there is no criteria, but diameter is actually governed by the air mass flow rate and the boundary condition is it has to maintain the minimum Froude number. Let us say Froude number 6 or Froude number 4, or sorry, 4 to 6, whatever you choose. So let us say I'm going with Froude number 6, and I have got certain airflow. So then using continuity equation, you can calculate your pipe diameter. Now, once you calculate your pipe diameter, then you can see that what's the pressure drop you are getting, and if it is too much, then you increase the pipe diameter. Then again, you have to increase your airflow. So it's a kind of two-way process. You go back and forth, and finally you come up with the best design. Another question we got is for myself is, let me go through it. Yes, what about step ups? So how do you step up? So the question is, how many pipe step ups should be there in a 1 kilometer long pipeline? Well, the answer is that it depends on what's the tonnage you are carrying and the type of ash you are carrying. Now, if I assume that your tonnage is typically say 120 ton per hour, and it's a 1 kilometer pipe, for that I would have 3 step-up locations. 3 step-up locations. So that means there are 2 step-up locations. That means 3 different diameter, maybe 250, 300, 350 NB sizes. Okay. Now the step up location, that's also another important issue. That was the second part of your question. What's the criteria? We actually I personally add around 10 to 15% of margin for every subsequent step up. So if I'm starting at Froude number 6, for the first one, I will take roughly say Froude number 7. For the second one, I will take Froude number 8. That's the minimum, or maybe little more, say Froude number 8.5 to 9, because what happens is down the line your ash, your air becomes thin. So when the air density is low, you need to compensate that by the extra velocity. So I will limit myself to these 3 questions, but any other question that we have received, I would personally email them the answers because of the lack of time. Now, Peter, there are a couple of questions for you, and let me just go through the list. Is it must to have air dryers for transport air compressors? So that's question number 1.
Well, and I personally recommend it. Refrigerated dryers probably adequate. I have seen some ash plants up in Queensland, Australia, where the company decided not to use dryers. They just used filters and drains. And I guess 80% of the year they don't have any problems. 20% of the year they have wet season, and guess what? They have blockages. So they decide to put up with that, and they want to save some money on the dryer. But to me, you're better off putting dryers in there to keep control over your humidity, because ash is quite hygroscopic and can stick quite nastily inside your system.
All right, thank you, Peter. The next question for you is, what are the type of recommended pads for the recommended fluidizing pads? Now, I don't know exactly this is at which place, but I believe this is for the blow tank. I don't know the type of blow tank he's mentioning, but could you please answer this in general terms?
It's not, yeah, it's a simple question, but a difficult answer. I mean, there's lots of different fluidizing membranes and pads around. I mean, I can tell you what we use. We've tried different air slide cloths and all sorts of things. And in industrial system, these things tend to fail. They break, they crack. And we use a special type of porous stainless steel in the fluidizing cone. And this we have found can handle the corrosive environment of the ash systems, particularly if there's a little bit of moisture around coming from the air, and it's quite durable, self-cleaning. There are different designs of these stainless membranes, and but the other factor that you need to consider, and this does affect the type of material and what size, is what sort of velocity you can put through these. So you've got to be mindful of the pressure drop across your membrane and what sort of velocity is creating that pressure drop. And so these things need to be sized and selected properly. That's the main key answer I can provide at this stage. But for a lot of systems we use, we like to pick things that last a distance, such as porous stainless steel. I hope that answers the question.
All right, Peter. And a last quick question: that do you recommend or not recommend top discharge blow tanks for fly ash?
For fly ash, it can be used. Anything bigger than half a millimeter, I would not use top discharge. I've seen product hanging around inside the blow tank. You won't get complete emptying of the contents, and that affects your system capacity.
All right, Peter. Thank you very much. And now we come to the last part of our session. And for this, I'm going to invite Mr. Deepta Sundar Mallik. Mr. Mallik, are you here?
Yeah,
Mr.
you
Mallik.
can. Am I audible? Yeah.
Yes, you're perfectly fine. So, Mr. Mallik, just let me just quickly put this to you. Like you have been associated with numerous material handling projects, including ash handling projects over the years. Since 1975, so over 45 years in DCPL and DCIPS as the executive director and head of the mechanical department. And I'm sure during this time you have worked with multiple customers across the country. So from your practical perspective and experience, which is a very large experience, we would like to know that what are the roads ahead you see and your final recommendation and concluding remarks.
Okay. Okay. We shall be limited to talking on ash handling system. Okay. You know that every plant has its own O&M group. They are good enough. They can solve day-to-day problems. But sometimes it is found that the nature of the problem is such that that is beyond them, because for every subject you have to have very in-depth knowledge so as to solve any typical problem. So what they do, they fall back on OEM. They call the OEM and their expert tries to see the problem and give a solution. Coming back to ash handling. In ash handling, what has happened? Firstly, no two ashes are equal. As Professor Mullik's lecture showed, that the ash can be very much varying from plant to plant, and therefore a standard design will not help every problem, every plant to solve their problem. So you need to know the ash and try to solve the problem as per the nature of the ash. That is one point, and therefore you don't have any simple medicine that if something happens then do this and that will be solved. These type of things will not really be fruitful. You have to have the knowledge, you have to have the diagnostic tools, and you have to have the laboratory sort of thing so that you can simulate the matter and then examine and then carry on research and then can find out a solution. This is one point of ash, that it is varying from plant to plant. The second problem, and that is a major problem related to Indian scenario, that in India about 15-20 years back we had at least 5-6 very good ash handling companies who had requisite knowledge so that any problem would have been referred to them and they would have examined the problem and could have found a solution. That used to be the pattern. But unfortunately, most of these companies have closed. I can talk of myself. I was working as general manager of DCIPS, which is a sister company of DCL, and we were doing ash handling plants across the whole country, and we are very reputed. And today our company is closed, and we have done at least 50-60 plants in the country. And the operators who are running the plant, if they find any problem, how do they solve it? They don't have anybody to fall back on. This is not only true for DCIPS or DCIPS, but it is true for many other ash handling companies which have been closed recently. And I don't want to name them one after another, but anybody who is associated with ash handling will appreciate that at this moment in India, there is hardly 1 or 2 companies who can really solve any troubleshooting problem. They can do something from their experience and can offer something. But when a troubleshooting has to be attended, then you need to have the proper knowledge on the subject. This knowledge bank is not available at this moment. So there was a big vacuum, and I'm very happy that BSII has come up to fill up the vacuum. And they have already done quite a number of plants, and I understand that they have worked with NTPC and have and many other companies, and have been able to offer the troubleshooting solutions. That is very good. I would say that there was a big vacuum in this particular subject, and that somebody has come up to fill up the vacuum is good for the country and good for the operators, good for the plant. I understand that there are about 200 listeners, and I'm sure many of them run the plant. And I'm sure that many of them are facing the problem in ash handling plant every day. So you are now getting a company who are basically researchers and academicians who can see your problem, work out a solution after rigorous lab testing and research, because their primary intention is not to make money or something. Their primary intention to serve the society and to make the plant run in the proper way it should run. Thank you. This is my feeling, and I share this with everybody. Thank you, Dr. Malik.
Thank you very much. And now we are, before we close for the day, we are going to organize another webinar, which is in our free webinar series, just like this one. And this will be on, we are just looking into the ash properties, how the ash properties can actually affect your design and subsequently your operation. So ensure reliability of operation for your dry ash disposal. Know your ash properties first. So we are looking into a date of November 19th, and I will send more confirmation in future. And finally, I thank all of you for spending this 1 hour with us. It has been a pleasure for us to talk to you. If you have any queries, please come back to us. We are located at Thapar Institute campus, Science and Technology Entrepreneurs Park, BSII Thapar Institute. You can send me emails to either of the email addresses, director@bulksolidsindia.com or ssmallik@thapar.edu, or you can ring me up. My phone number is provided. So that's all today from our side. I hope you have learned something from us, and if that has been the case, we'll be very, very happy. We will think that we have contributed something positive in this session. Thank you.